see you now. Yeah, so Dr. Hadi Sadati. Dr. Hadi Sadati is a CME Research Fellow at Robotics and Vision in Medicine Lab of the Department of Surgical and Interventional Engineering at King's College, London, investigating the theme topic, reinventing catheters by soft robotics for autonomous robotic thrombectomy in acute stroke. He has a master and bachelor in mechanical engineering from the Sharif and Amir Kabir University of Technology of Tehran in Iran in 2010 and 2012, and a PhD in robotics from King's College, London in 2018. He has been a postdoc research associate in robotic system engineering at RFIM Lab in 2019-21, and in morphological computation at University of Bristol in 2017 and 19. He has been a visiting researcher at Learning Algorithms and Systems Labs in Switzerland at EPFL in 2019, the Department of Electrical and Computer Engineering at Clemson University in 2017, and at Dyson School of Design Engineering at Imperial College London. His research experience and interests are in the field of soft robotics, medical robotics, morphological computation, morphological contribution to inspiration, system dynamics, control, and mechatronics. And today he's going to introduce the TMTDyn Matlab package for modeling and control of soft robots. So Hadi, the floor is yours.
Thank you so much, Matteo. Thank you everyone for attending this workshop. Personally, I'm very pleased being part of it, presenting my work, also hearing from fantastic software developed by Federico's team. Really congrats to Federico and his team. Okay, let me share my screen. So today I'm gonna present TMTDyn package. It's a MATLAB package for modeling and control of soft robots. Matteo has already introduced me. At the moment, we're focusing on eye disease using fine continuum manipulator tools that we call concentric tube robots. You can see one of these in play here. And as you may anticipate, it includes design, modeling, safe path planning, and VR-assisted robotic design and verification. So that's a bit about me, but let's jump into the topic of this workshop, soft robots modeling and control. So it's fine to model them when they're doing the slow static motions in planar. They exhibit small bends and no external loads are in place. But as soon as we get fast dynamic motions in 3D with complex bends, you get like this. It's really hard to handle. So I did literature review during my PhD. There has been long system approach, constant curvature with Euler-Bernoulli approach, constant curvature dynamics, Kosovo-Rod statics, and later on dynamics, and finite element approach implemented by the time that I got into the field. Since then, we've seen identification shape functions to capture the kinematics, shape parameterization, partly done by me, partly by Singh and Franz, finite element model order reductions to bring reduced order dimensionality to finite element models, shape parameterization based on Bishop frames more recently, and also strain parameterization. Well, I named it strain parameterization. Sorry, Federico. Federico called it piecewise variable curvature approach that you've already heard about. Well, there has been a lot around, and it has been a cumbersome task to do to model continuum manipulators. So I started thinking about reduced order dynamics of these systems. More specifically, You have a continuum robot exhibiting complex deformation and also more complex deformation when external forces apply. So I thought maybe I can capture the backbone kinematics like a polynomial curve. As a result, I could I introduced reduced order dynamic modeling in 2018, almost at the same time. Professor Duriez at INRIA, they were developing their model order reduction techniques. And I noted that it actually provides the most accurate of all results with a small number of state space. Later on, I implemented that in a package called TMTDyn. It has been in development for a few years now. I started with pneumatic continuum manipulators, showcased it with, later on for whisking robot. You see some of the simulations here, and later on for modeling spider web, like two-dimensional systems. So the package I'm going to present you, it delivers equation of motion theoretical derivation for the system. So that's the main advantage compared to learning-based approach or finite element approach. And different kinematics are implemented: reduced order, different types of discretization, and series link rigid robot kinematics as well. And you can handle geometrical constraint, tendons, pneumatics, hydraulic actuation elements. And it benefits from a MATLAB-based domain-specific language interface, which I hope makes it easier to model the robot and define the robot. More recently, these are unpublished work mostly. Tendon actuation and inverse controller design for tendon catheters are implemented. Concentric tube robots with unstable behavior, as well as concentricity constraint is investigated, and also growing robots with multiple structural properties, like growing sheath with an internal tendon-driven catheter. Please get in touch or follow my publications to know how they're implemented using TMTDyn. Okay, but about TMTDyn itself, let's cover a bit of theory. When I want to model a continuum manipulator, not sure why it's here. Okay, when I want to model a continuum manipulator, I would like to think about two key elements: the modeling assumptions and the solution strategy. You have to define your kinematics, system mechanics, or governing equations, or basically conservation of laws, and material mechanics, constitutional laws. System kinematics is like if you go discretize, reduce order, etc. System mechanics is like if you go for Koszorot rod, Lagrange, and material mechanics, it's like if you consider Newhookian, Hooke's law, Gantt models for the material, etc. And the solution strategy, you can approach it directly. Usually, you cannot do that because you end up with boundary value problems with continuum manipulators, or indirectly in an optimization framework. But you're going to see, and you've seen in Federico's presentation, that you can formulate a direct problem for the dynamics if you choose the reduced order model approach. You can have a look at our preprints to see more in details. I'll leave it here for now. Speaking of kinematics, so we can start with differential kinematics, usually being used with Koszorot rod models. We can take two approaches. We can discretize it, or we can use a continuous reduced order description. If we discretize it, series link rigid robot style, we know about it. We can do Euler Bernoulli beams with relative states. It's quite similar to Federico's earlier work on piecewise variable curvature and piecewise constant curvature approach. So basically, you assume a constant change of curvature and strains along each beam. Or you can do Euler-Bernoulli beams with absolute estates. It's basically finite element approach, but implemented in a unified framework similar to the other representations. So we can later on drive the system dynamics and use it for controller design. So basically, Euler-Bernoulli with relative states is very similar to series rigid link robot, but Euler-Bernoulli with absolute states is really similar to finite element approach. The other way is taking the reduced order model. We can capture the backbone shape with a polynomial with or any other fitting approach that you may see fit. We can define the orientation based on separate polynomials, or we can extract that from the curve itself. A new bishop frame is implemented, for example. Or we can parameterize the curvature, not the shape, as implemented in Sorosine, presented a few minutes ago. In TMTDyn, you get all of these presentations. You can choose whichever you want, except the curvature parameterization. So use Sorosine to use this very clever, fantastic approach. Have a look at TMTDyn for the rest of these kinematic implementations. A bit of theory. I'm gonna wrap it up fast. I use quaternions. I define the quaternion multiplication and quaternion rotation as presented in the standard textbook, and introduced cross superscript and asterisk sign to basically summarize the relation behind that. You can, if you follow the hand notes, quaternions, you can simply replace them with rotation matrices as well. And here on the left bottom side, you see the differential kinematics, usually being used by alongside Kasrat-Rod model, implemented based on quaternions, as well as rotation matrices. You may want to follow Caleb-Rocker's publications, who is using mostly this implementation. When we talk about series rigid link robots, it's like rigid links in rigid robotics, rigid link robotics. So you have a rotation matrix. You want to calculate the next rotation based on the previous rotation, or next quaternion based on the previous one. There are different implementations here. One is based on Lie algebra and basically linearization of the differential kinematics. The other one is based on Euler angles with different order of the rotations. And the last one is basically, it's very similar to the linearization of the differential kinematics presented by, well, Federico is an expert there, but in the Lie algebra formulation itself. But it's really similar to just linearization of the differential kinematics itself. Euler-Bernoulli beams with relative states. You need to use forward maps to find the next rotation quaternions based on the previous ones. So Qi plus 1 based on Qi. And here alpha and epsilon are the bending twist angle and deformed position vector. Again, equations are provided as you see here in a nice closed form, and you can proceed with that. In a reduced order formulation, we substitute the kinematic with a polynomial. And here, the polynomial, I present a closed form for that polynomial based on constants, a constant matrix C, and a few shape functions S. Here, shape functions are basically S, unit length to the power of 0, 1, 2, basically to the power of I. And you can define the orientation and position based on separate polynomials. Then you need to use inverse kinematic map. to find the strains based on the shape, the parameterized shape that you've introduced. So basically, based on these polynomials, we know the current orientation and current position. So we use this inverse map to find the strains that we need that we need for calculating the deformation energy of the system. We can define a Bishop, we can use Bishop frame. So instead of parameterizing full orientation space, I mean all of the elements of a quaternion, we can just define a twist angle, extract a tangent curve, a tangent frame based on the curve geometry, and just impose the correction twist angle on top of that. As a result, we end up with less a number of polynomials, because to define the orientation, we don't need to define all of the elements in a quaternion or Euler angle set. We just need to define the twist angle. But again, we need to use the inverse map to calculate the strains in the system. And curvature parameterization, again, we use polynomial representation, but instead of defining the full shape, we define the strains, curvatures, and torsion along the manipulator. So again, C is the coefficients, time variant coefficients, S is the spatial shape functions, but this time the results are the strains and curvatures and torsion. So as a result, we use the forward map. We now have the curvatures and strains, and we need to calculate the absolute orientation and position based on that. You see that an extra integration step is needed to get from curvature to the absolute positions. While in the reduced or in the shape parameterization, a differentiation is in place. And usually differentiation, you can handle it easily, theoretically, but integration, there's no solution for that, no easy solution for that, so you need to handle that numerically. There are advantages, disadvantages in using these methods. There is no publication about that, but I encourage the community to have a look at that. Okay, final notes. We have these two approaches. Reduced order model, when you parameterize the shape, is very similar to using Euler-Bernoulli beams with absolute states. Basically, it's really similar to finite element technique, because here the system states are the absolute states and orientations. But when you choose the curvature parameterization, series link kinematics, or Euler-Bernoulli beams with relative states, it's really similar to traditional robotics, rigid link robot kinematics. You use with relative states. The advantage of using relative states is it usually matches your actuator space, and you end up with the minimum number of coordinates, basically the generalized coordinate, as Federico mentioned. But the equations tend to become very complex and lengthy. But the finite element approach with absolute states, you end up with repeating similar equations, similar smaller equations, so less complex. It gives you more flexibility to play with numerical methods, and as a result, it's less sensitive and more robust to numerical calculations. But the reduced order model, when you parameterize the whole shape, benefits from as well. Then talking about dynamics, we can take the Lagrange formulation path, or we can take an alternative method called TMT method. It's not very familiar in the community. But both ways, you end up with a cause vector form for the dynamic of the system. Basically, mass matrix, accelerations equal to the right hand of the equation, and you can formulate a basically numerical integration scheme to solve it. But as you see, the TMT method requires less steps and no collection of coefficients needed. So it's really good for, it's really beneficial to use TMT method for if you're developing a software. It is basically, the TMT method is based on principle of virtual work. As again, Federico, so I'm basically citing him a lot, mentioned, you end up with less complex equations compared to Lagrange. The only difference with principle of virtual work or principle of minimum energy is you drive the matrices directly. You drive the whole thing in a vector form from the beginning. So it's basically a matter of a different implementation. In the TMTDyn formulation, you end up with a summation on all the elements in the system. The mass matrix you have to form based on Jacobian transformation from the Cartesian space to generalized coordinates based on the states that you chose to model your robot. The Coriolis and gravitational terms, it combines the Coriolis terms and forces due to gravity, basically forces directly in the Cartesian space. And conservation and non-conservation terms, these are coming from the compliance, deformation energy, viscoelasticity, and internal actuation. The good thing about the summation is you can calculate these separately and then just sum them over. It's not like Lagrange that you end up with a large equation that you need to calculate at the same time. The continuous implementation is just substituting sigma with integral. That easy. And I just want to point out, ending up with the vector form for the dynamic system, you can easily manipulate it into inverse formulations. You need that for handling constraints, parallel and closed loop configurations, and designing controller and observers. For example, here, this is the mass matrix. TC is the Jacobian transformation from the constraint defined in the Cartesian space to the generalized coordinates you chose. Lambda is Lagrangian multipliers. DC and DC is basically the terms appear from 2 times time differentiation of the constraint itself, and U is, it can be your PID law for example, a trajectory tracking task. And D and W, sigma D and sigma W are the terms you saw in the system dynamics. We've already implemented inverse Jacobian feedback linearization, load compensation formulation with this. So basically for a controller and observer formulation, you just substitute TC with the actuator space transformation and lambda with the actuator input itself. And or the unknown force or the unknown state that you're observing, and it solves alongside the rest of the system for you. Okay, some numerical results. We did some comparative study based on experiments with stiff flop. It's basically a silicon continuum appendage with 6 braided pneumatic actuators implemented inside a central hole, and the actuators are placed on a certain with a certain distance from the center. And we did force free and with torque and point force exerted along the robot and at the tip. So first, comparing lump system approach, constant curvature, modified constant curvature, Cousin beam, and shape function methods. You see that lump system, basically rigid link kinematics, it's good for nonlinear controller design, but not accurate. Constant curvature, it's not accurate, but it's really easy to implement structural details like the braids of the actuator, the change in the cross-section. The modified version improves the error, but not that much. Cousin rod is the best in terms of accuracy and generality, so it's robust to the changes. but you cannot formulate it in a control in traditional nonlinear control way. And shape function identification based on Isuru Godage's fantastic work. It provides very good accuracy and it's real time, but actually formulation and the formulation and accuracy is limited to the training data set. So it basically suffers kind of from similar disadvantages of learning method, which relies on the richness of the data. And considering the exact braiding model and exact cross-section model improves the accuracy of the models by 3%. I'm going to talk about that a bit more later. Talking about the Euler-Bernoulli beam with relative absolute states reduced Euler model and series link implementation again, we could achieve between 4 to 14% in dynamic simulation and 8 to 19 in static simulations with these different methods. We observed that Euler-Bernoulli with the absolute states, basically finite element, the model which was really similar to finite element, it gives you less complex derivations. The series rigid link, the traditional rigid link robotics, it gives you the worst derivation and equation optimization time. So you end up with a long set of equations to handle. And reduced Euler model is slightly better than Euler-Bernoulli with relative states in terms of the complexity of the equations, but not as good as Euler-Bernoulli with absolute states. In terms of accuracy, reduced Euler model is the most accurate with the minimum possible number of states for the system. And it's less sensitive, very robust to numerical instabilities and incorporation of hyperelasticity in the system. But it's computationally expensive for higher orders, and convergence may not be guaranteed depending on in the curve shape that you choose. Euler-Bernoulli with absolute states, basically finite element model, it's the most computationally efficient one, and it provides good accuracy, but you need large number of segments. Having a look at the plots, you see the same, for example, for the dynamic simulation, no load, you get the same accuracy as, and blue line is the reduced Euler model. You get the same accuracy as the reduced Euler model with with polynomials of order 2, but with 4 segments if you choose the finite element approach. So 4 segments means at least 2 times more states in your system to deal with if you want to design a controller. So it's accurate, it's fast, but you end up with way more number of states in the system. Euler-Bernoulli with relative states, it's the most sensitive alongside the rigid link robot to the changes to the implementation of hyperelasticity and changes in the system. And in general, dynamic simulation and cases without external loads are generally more robust. So if you're looking into more higher robustness in your simulations, it's better to approach it in a dynamic way rather than a static way. I assume the reason is obvious because you're aware of the history of the motions as well. Speaking of the sensitivity to implement it to considering hyperelasticity, you see where the simulations diverge numerically for these different cases. So basically, green is when the hyperelasticity cannot be considered, and you can see that with reduced Euler model, it's pretty robust, so you can handle it. Also with finite element style thing, the EBA, Euler-Bernoulli with absolute states. But as soon as you use relative states, it becomes sensitive to change of parameters, introducing nonlinearity in the system, etc. That's so my favorite is basically Euler-Bernoulli with absolute states if you don't design a controller, and reduce Euler modeling if you want with parameterization of the shape, of course, if you want to do the control design. But it really depends on your application. Series the relative state definition, it has a lot of advantages in terms of implementing internal constraints, and etc. So it really depends. Some special notes. We can look at the exact deformation of the cross section. So we can use hyperelasticity and constant volume constraint to find how much the cross section changes when the length of the unit changes. And we had that issue in a stiff lob. It was really floppy and soft structure design. And as I said, it increases the accuracy by 3%. Different methods are discussed. The simplest one to a more accurate one based on Mooney-Rivlin problem of flexure, which we investigated and improved further in a publication back in 2017. So you see the cross-section can slide as well as expands toward the bend and shrinks outward the bend. And you see the different simulations and in comparison to the stiff lob cross-section, and you see the case considering the sliding the material and disproportionate disproportionate distribution of the material after bend actually matches the cross-section pretty well. But the improve you get from exact model of the cross-section is less than 1%. So just capture the cross-section change to benefit from 3% improved accuracy, but you don't need to go much further. Also, we can implement the cross-section change due to introducing braid constraints. We can go with the exact implementation, but we can assume that the braids are so dense that the pitch angle of the braid doesn't matter anymore. As a result, the cross-section, the internal cross-section of the actuator remains constant throughout the actuation. So the actuator elongates, but the internal cross-section doesn't change. It's the thickness that shrinks to compensate the deformation while preserving the volume. Again, different comparisons. You may have a look at the conference paper I had a few years ago to see different implementations of cross-section deformation and braided manipulators there. Some final notes. Simplifying assumptions, it's easier to understand and implement. It has computational performance, and it's robust and less sensitive to variable changes. But usually you observe higher identified values for elasticity and smaller deformation energy being predicted. Results are incorrect for large deformation, obviously. And you see incorrect trends in sensitivity analysis if you're doing design. A high fidelity model, it helps you with understanding the underlying principles better, but you need to choose how much in details you want to be. You can verify the regional validity of the simplifying assumptions. So, and you can use the simplified models accurately in those regions. But instability arises with complexity in the equations. So my suggestion is avoid complex derivations as much as possible and implement what you really need in a simple way. And they're computationally intensive. Implementation is hard as well. Okay, that's a bit on the theory. I want to jump into the software implementation itself. Our experimental setup, what we are going to model is the stiff lob. So basically, it has an overall silicon body with internal ports. So outer radius, inner radius of a cylinder, 6 braided pneumatic actuators implemented with an offset, this small offset, inside with this fixed offset from the center and soft caps at both ends. The experimental setup looks like this. We have a continuum appendage and a force sensor with basically a rigid body at the tip. And the case includes force-free external, basically free deformation of the setup without external force, and when an external force is implemented at the tip, we try to keep it as a point force, but not possible. So you're going to see the implementation of general forces and moments in this case, and you see the complex shape. So it's not goes to constant curve anymore. You get a S shape if the force is large enough, and it's combined with moments as well. And for the sake of just representation, I'm going to discuss Euler-Bernoulli with relative states. Why I chose this, although I like the finite element-like approach, the Euler-Bernoulli with absolute states or reduced Euler model, is basically using constant curve method or using series rigid link robot kinematics, you end up with singularity issues. But when you use Euler-Bernoulli beams with relative states, basically using strains to formulate the transformations, it's especially in a Bishop's frame formulation, like assuming curvatures around materialistic frame axis X and Y, it solves the singularity issues associated with constant curve and rigid, rigid link kinematics. So let's see how it's implemented. And I encourage you, if you stick to these methods, follow this. Don't take my word. You can follow up Caleb Brooker's presentations in the past year and so on. And he's one of his main pitches as well. Federico and Caleb had a lot of good publications on this, showing the advantage of basically taking these kinematic approach compared to constant curvature approach. Okay, that's it. Let's move to the software implementation itself. Just for the sake of reference, I keep this figure open. I can answer a few questions like for 2 minutes before jumping into the software demonstration itself. If there is any.
Is there any question from the audience? Come on, don't be shy.
Yeah, can I have a quick question?
Go ahead, please, Nan.
Yeah, thanks, Prof, for the theoretical introduction. I found very interesting. Just a general question. I found in a table, you compare all these arrows. In general, all the arrows are pretty large. Like even the smallest one can go up to 60 or 50%, which is significantly large compared to kinematic of a rigid body robot. Just generally, what's the reason of this per performance for soft robot modeling?
Yeah, so not general soft robots. Blame a stiff flop complex shape. So you see that, as I said, see how the cross-section changes. And in most of these models, we don't capture that perfectly. And also see the complex design. So you have 6 braided actuators implemented in a wobbly soft structure. And the structure is actually not long, not really long. It's 50 millimeters long. The active part is 44 millimeters. So you have to silicon caps at both ends that you don't have any control on. And when you calculate the accuracy in percentage, you divide the accuracy of the tip, the absolute error, divided by the length. And usually divided by that small length, you end up with large errors. But for example, if you have a look at Octave, and 16% error that you see, it's associated with 5 millimeters absolute accuracy. And 4% error, it's associated with 2 millimeters absolute error. And 2 millimeters for this wobbly structure is actually really good. But in terms of percentage for this structure, it shows large values. That's why you need to do learning-based methods on top of theoretical models or PID implementation to achieve high accuracy in controlling the soft robots. There you can achieve like 0.5 millimeter really easy with a PID implementation on the top of the model. So basically the model gives you generality, robustness, and a secondary controller on top gives you accuracy that you want. The state of the art is around 3% in the community, the mechanics-based modeling. Okay, the example that I'm going to show you, it gives you 4% accuracy. You're going to see it.
Okay, thanks a lot.
Yeah, thank you for the fantastic question. Okay, so to download the package, I want to direct you to the TMTDyn GitHub page. Here is the address. Here you see various versions of TMTDyn from 2015 when it was only rigid robots. Then I improved it, and the first publication came at 2020. Since we've implemented the interface, a growing robot, Mamobot, the concentric tube robot, the unstable robot with concentricity constraint, and the latest stable version. So beta versions they have more functionalities, but the latest stable version with some examples. Okay, some general explanation here. You just need MATLAB software. You don't need to install anything. Some efficient simulation tools are already integrated, but a wrapper for using sundials solvers is provided as well. And you may know that this is one of the most efficient numerical solvers for ODEs and BVPs out there. To use that, you need to download and install sundials. We won't cover that. Just get in touch if you needed real-time, very fast simulations like that. Okay, let's click on version 6, latest version and examples. Okay, and as it says, we just need to download the zip file provided there. Okay, just click on the file, click download, and just download it anywhere that you want. Okay, we're done here. This is where it is downloaded. You just unzip. Extract here. And you can just delete the zip file, doesn't matter. Okay, what you see is a few M files, and these are basically different implementation of the kinematics of the stiff-flop that I explained. Here you see the reduced order model, Bishop frame implementation, and SP-line implementation as well. These are under development work. Sample experimental data is provided if you want to investigate your theories further. And to run it, it's as easy as just opening MATLAB. And just open one of the files. So I'm going to talk about Euler-Bernoulli with reduced order states. That's the file that you get. You can just hit F5 and run it straight away. But before that, let me show you the structure a bit. So you get, so disregard the EOM, all of these files. They're basically provided for you. It's actually provided there, so you don't need to rederive the equation of motion. Okay, so you just even delete that. The equation of motion folder is where you get the equation of motion derived. It already has a few folders and files in it. The CodeGen folder has the wrapper for external solver. I don't talk about it. But you can you see a post-process.m file. It's basically the post-process that you want to do. You just write whatever you want in this code, including the error analysis. You're going to see it. And a static and dynamic mid steps. That's where you can interfere with the simulations during the integration. You need that to incorporate hyperelasticity, changing the cross section, changing the PID values, feeding the input, or changing the actuator inputs. So that's where it happens. But you see the folder is almost empty because nothing is derived yet. Experiment is the sample experimental data provided. HLL is the high-level language interface. We're going to talk about it. Results is where the results stored. These are already there to give you some hint of the previous result, but you see it empty if you start straight away. And TMTDyn is the core of the package. We don't need to look into it at the moment. Okay, let's have a look at the implementation of a stiff flop in our package. I keep this aside here so you can have a reference while I'm going through it. It's like a config file where you define your robot. The first few sections is irrelevant of TMTDyn package. It's just where you define the parameters, set the variables, etc. So like parameters, here NL is the number of segments. Here I set it to 3 for the sake of being able to drive it in a short amount of time in front of you. But you can set it to higher values. Then you need to wait for the package to drive, optimize, extract the equations in C format, and provided you with the final equation of motion to be simulated. Structural parameters, the length of the segments, internal, outer, external radius, internal, external radius for the pneumatic chambers, the braid thread thickness, the lead angle for the braids, the position, the diameter of radius of the position circle for the actuators, the offset of the actuators with each other, and this is basically the placement of the actuators around this circle. This is a simple rearrangement. Don't worry about it. Mass of the force sensor, length of the rigid link at its tip, radius of the rigid link, gravity elements, density of the silicon, modulus of elasticity, a power law for the viscous damping, so you can implement rate thinning, rate thickening, etc. And damping values for shear, elongation, bending, and torsion. Okay, these I set absolute values here, but you can set proportional values, and the software basically takes care of it automatically for you. But here I set it absolute values. Next section is the parameter, the variables you want to have in your derivations. You don't need to define these variables. You can assign absolute values to them. But as soon as the robot equation of motion is derived, those values are set. You cannot change them unless you derive the equation of motion. It's a lengthy process. But if, for example, you want to test your design, etc., you can set any of the parameters that you want as variables. After deriving the equation of motion, it accepts different values, variable values for these. Okay, so that's one usage. The other usage is you set the variables like input force, torques, and input pressures that, well, these are not design values, but you need to change them during the simulation anyway. So I define symbolic variables to be changed later. I pass them through a vector, and vector vals is basically the initial values for these variables based on the parameters I introduced further on. This is where the experimental data is extracted and being passed. I just store them in a user underlined Parse variable. Just keep in mind the name later on. you need to reference that in the dynamic mid step. Remember, this file interferes with the values during integration. And here you see that I use user parse, underline, etc. to extract the current value for the forces and actuation pressure. So everything needed is passed here. Then I do some pre-process. It's basically calculation of the area, calculation of, for example, here you see the calculation of the radius of the pneumatic chambers based on the constant volume constraint and braid constraint. So this is the equation for it. Also, the moment of inertia, stiffness matrices, moment of, second moment of area, moment of inertia, the same for the tip rigid body, the force, the pressure vector, P1 to P6, the tip force vector, the force associated with the pressure, which you see it's along the axis only, it doesn't produce any shear, and also the moment associated with it, and then the force at the tip. So again, you can define them based on numerical values. You can define them in the interface itself, but you can define them beforehand to keep it clear and clean. Just pay attention to lambda. Lambda underline is a variable for a stretch ratio of the appendage. So changing this value, you can introduce hyperelasticity into your model. And based on that, you change the radius of cross section, the length of the elements, etc. So that's a way of introducing hyperelasticity. And later on, you see that I basically change lambda in simulation time. Here it is set to 1, but you can basically uncomment or change the derivations here based on the states, etc. to keep it work. Okay, everything I said wasn't part of the TMTDyn. It's just a way of keeping the code clear. But from here, it's the DSL implementation of the robot in TMTDyn package. The distributed, the domain-specific language or the high-level language implemented here is implemented in a way that when you read it, you understand the implementation, and it gives you like a flow or a continuous read through the configuration file. So that's an advantage in having such implementation. You see separate parts that I have results equal, and again here, that's not needed, except you use MATLAB version 2019 and forward. At that point, MATLAB decided to not support very long statements and basically very long statements like this. So it's just introduced the way to prevent MATLAB from that crash. And also it gives you some nice segmentation of the code. Okay, let's see what it is. It says TMTDyn simulate with variables vars and var values and user parameters use parse and drive the equation of motion. I said no here, but I can set different values here, like drive the full system for you or assume a small velocity. So it disregards the Coriolis forces. If you have a large system, you can do simulations faster. Optimize the code for me, then perform an analysis and a static analysis. For that, generate MEX files. Okay, there are other options. You can have edited M file, generate M file, and use old MEX file, etc. So using MEX file is more efficient. It takes more time to generate, but it gives you faster simulation. For these time steps, then do dynamic simulation. Again, generate a MEX file for me. This is where you introduce the solver. I used Rodo. Rodo is a very good solver compared to MATLAB solvers, but you can set it to, for example, MATLAB and use ODE 115 instead. It's actually Rodo is faster, so use this. But again, other options are available, like using sundials, DAE, and ODE MATLAB implementation. It's not as fast as the external C implementation, or use external. It calls the wrapper, the C wrapper that calls the sundials ODE external for you. The good news here is you end up with equation of motion in C. So you can implement it in ROS, in your real-time framework, etc. So it gives you equation of motion in both MATLAB and C. A start time, end time, a sample rate of 100, and report time intervals. It basically shows the simulation progress. You can basically delete it. It just, you don't see anything until the simulation is finished. I set it to 1. Every 1 second shows something. Then I want to post-process, animate it with tubes, show the frames, and some values for how many edges those tubes should have. So you can control. Record the video for me. Report it only once. It waits, if you set it to 1, it waits for the simulation to end and then animate it. But for example, if you set it to 1,000, it divides the simulation time to 1,000 steps and basically interrupt it, show the simulation, show the animation, continues. That's a way of having an interactive simulation. But I set it to 1 and run user code. And you remember that we talked about the post-process code in the EOM file. So whatever you write here, it just runs for you at the end. Okay, these are general stuff. To comment them, just replace the 1 dot with 3 dots. Okay, I'm going to show you where you get a reference for this. This is actually just a small portion of everything that's implemented there, and basically a very basic portion of that. But let's move to the actual robot itself. So I have a board with gravity G, X, G, Y, G, Z. My robot name is series rigid link arm. Okay. Well, actually, the name is not correct. I have to set it to like Euler Beam with relative states. Okay. Doesn't matter. It doesn't change anything. The robot has a few elements, and you see it's in the indentation says that for example, the body is associated with this robot, and the mass is associated with this body, etc. Let's see the elements of the robot. We have a body, which is a stiff flop. Okay, sorry for the naming. Probably slipped through my attention. Okay, we have a body. The first body is the stiff flop. Then further ahead, we have another body, the tip force sensor, and we have an external load. I name it tip load. The name doesn't matter, just for your reference. And then run it for me. Okay, these are the elements. Let's see what each contain. The body has a mass, has an inertia. It has a center of mass position at this location, and the tip is at this location, and it has a cross-section radius, which you see lambda is implemented here as well. So you see the variability of cross-section as a result. So that's the inertial parameters. The body is connected to repeated joints. So basically, I define a single segment, and I repeat it multiple times, because it's basically, when I break it into multiple segments, every segment is a copy of the previous. So repeated joints, 1 to NL, the number of links. Then this connection is with transformation from a body. So where is the first end of this joint? So the second end, we know it's connected to a stiff flop body. But the first end, so you see I set 1 here, comma, and a vector. 1 means connect to the first defined body. And the first defined body is the stiff flop itself. So it basically says connect each segment to another segment in the same body. But which segment? Yeah, that's the vector. It's 0 to NL minus 1. So basically connect each segment to the previous segment, and 0 is ground. So basically it connects the second segment to the first segment, etc. What are the transformation for this joint? We get a transformation along z-axis. Let's show it here, why we have a transformation along z-axis. So see, the next mass is transformed with respect to the previous mass with a certain amount. Okay, that's where the transformation comes. But for the first link, the mass is exactly on the connection point to the ground. So for the we have this transformation along z-axis, along the main axis of the robot, except for the first link. So that's how it's defined. You define a vector of transformation for these copies separately. So you can have as many copies as you want and have some control on different properties of those copies. It says, don't set this translation along the z-axis to 0 for the first one, but then set it to L underline SS, which is the length of the link for the later ones. Then we have a transformation with X, Y, and Z set to infinity. It means that all X, Y, and Z directions of that transformation are degrees of freedom of the system. If I set it to set one of them to 0 or set one of them to something else like 10, that becomes a constant transformation. And the system automatically actually assigns the state space you require to where you define inf. Okay, so that's how you define the degrees of freedom transformation in a transformation. Then you want to define the properties of each degree of freedom that you define. The first degree of freedom, I want a direct input of type force with value previously defined. It's along X. Basically, we are defining shear for each element. It has a parallel spring and parallel damper. The parallel spring, the constant comes from the elasticity coefficient for shear and also for viscosity. It has a power law as well. Second degree of freedom, the same. It's for shear along y-axis. Third degree of freedom, the same. It's elongation along z-axis. Then on top of that, I have a rotation of type strain. And you saw that closed form derivation for that in the slides. The strains, again, I set all of the strains to inf, so meaning that all of the strains are degrees of freedom in the system, and a quaternion initial value as the initial value for the simulation. Again, for each of these degrees of freedom defined, I said degree of freedom 1, 2, and 3. They have a direct input of type force. Well, it's the fourth element of this this vector. It's basically the torque. So degree of freedom 1 is a strain around x-axis. That's basically a bending. Degree of freedom 2 is a strain, a rotational strain around y-axis. That's basically a curvature, a bending around y-axis. And degree of freedom 3 is a rotation, a strain around the z-axis, the main axis of the robot. It is the twist, torsion. Again, I can set the input, the spring, and damper coefficient for that. Okay, you can set the direct input as position. When you have a force, it's like a direct force, but when you set it as position, it's like defining a geometrical constraint for that joint to move exactly like that. You see that I can define any rigid robot with this formulation as well. It's basically a way of formulating a robot, a continuum robot. But for a rigid robot, definitely you don't use strain, you just use rotation, and that gives you Euler angular representation. Okay, done. The last part is the second body, tip force sensor. It has a mass, inertia, center of mass, location of the tip, cross-section radius, and it's connected to body 1, basically the previous body defined, but segment NL, the last segment of the previous body. And it has a transformation LSS, so it's connected at the end of that segment. Then we have an external load, it's tip load, it's exerted again on a body with a certain transformation. Which body? Body 2, the second body that's defined. It's the force sensor. The transformation is 0, 0 LF. It means that basically an offset from the base up to the link to the tip of the link, that's the length of the force sensor and mounting. And these are the forces being exerted at that specific location. All of these parameters you can change. Okay, the force certain values, moment certain values, and then you hit run. Let's see how it works. So I just hit F5. It gives you some feedback. So experimental data is loading. These are the experimental data. Then it starts driving. It's basically driving the equations for the first joint. Then the second joint. Now it drives the inertial elements. B counts means the body elements. Then it drives the external, the elasticity, drives the external load. I found 4 masses because we had 3 links for the stiff lob and 1 force sensor at the tip. Number of springs implemented, no constraint, 1 external load, and 18 states. So 3 multiplied by 6, 18. Now it starts a parallel computing toolbox to basically drive the equations, optimize them, save them as separate functions, M-file functions, and then convert them to a MEX file for you, okay, to run as a C code. Okay, it takes some time, and as I said, models with relative states, it takes a lot of time for the derivation. You end up having long derivations for when you use relative states like curvature or angle values. If I run the Euler-Bernoulli with absolute states, you would see that it ends sooner. But I told you I just wanted to showcase it, this one too. Okay, let's see what's happening. If I go to the file, if I go to this folder and I go to the equation of motion, you see now the equations are being derived. And some of them, basically, this is 0 kilobyte, the size. So it's basically the equation that is being derived and optimized at the moment. The other ones that are already derived, you can always click and open, and you see that MATLAB has already introduced intermediate coefficients to simplify the derivations for you. That's why I said it to optimize the code for you. And these are the final derivations. Keep in touch if you're interested in the details, but it basically gives you the inertia, transformation maps, everything that you may need later. Okay. While it is driving the equations here, let me talk a bit about where you can find references to the methods you can use. So in the HLL folder, we have a file called references. The reference folder, it basically stores all of the possible methods that you can call. Okay, basic explanation is provided in front of it. So I assume if you want to get creative, you have to look at the examples provided and also get in touch. Sorry for that. Most of this work is under development, but you get very cool features here. For example, you're gonna find a reduced order model. So for shape parameterization, you get that. Okay. Just tell you that it finished the derivation. Now it's saving the necessary MEX files. It finished that. Now it goes for equilibrium, the static analysis. Again, it drives the equation of motion in MEX files for you. And you're going to see the static analysis results soon. Okay, but getting back to the references, so you can implement reduced order model. You can implement the constraints like concentricity using various ways of implementing geometrical constraints implemented here. Also, you can define unknown direct inputs for controller design, set PID values. You can set direct input values if you want to set geometrical constraints, and etc. Other stuff. Also, so yeah, while I was talking, the a static simulation is derived, solved, and the results are shown. There's a recording for that I'm going to show you. And also, for example, if you have a tendon in your robot, you can set the PID values to control that tendon. You set desired geometry to your beam, or you can fix certain directions if you have a constraint system. Also, with the same constraints, you can implement parallel robots, constraints with sliding against the wall, etc. And you can have a mesh like a fabric or a spider web. External loads, you can observe them, for example, unknown directions or unknown external force values. So just get in touch if you're interested in further implementation. I'll show you some examples. Okay, let's see what happened here. The static analysis is derived. The static solution is found via fsolve. The result is provided to you, so you check if it is actually converged based on exit flag and also the error of the converged value. And I had, I think, 7 points for static analysis here. Okay, but after that, it basically moved to driving the equation of motion for the dynamic system, and drive a MEX file for that to make it faster, and then just showing the progress of the simulation that you see here. So we said we want to see every 1 second the progress. We have 50 seconds of simulation. You see it's almost done. It's done. It calculates the animation. And now you see the animation here. Just note that the animation is slow because I'm recording a video of it. Okay, if you set the video off, it becomes faster. Also, if instead of showing tubes, I show the animation with lines, it's faster. If I turn off the tip references, it becomes faster, etc. Okay, you see the animation, and it's in play. But and it's going to show you the animation, store the result, etc. Meanwhile, we have the you see the animation. These are based on actual experimental data. Let me show you. So we've already derived the equation of motion, right? So we can set this derived equation of motion to no for further analysis. Again, since I define all of these values as variables, I can change all of them if you want to look at the effect of the parameter value change. Or I can send a new experimental data like sequences of pressure values, etc. The lengthy process of derivation is over. You don't need that anymore. But as a result, you cannot mess with the robot definition anymore because it doesn't redrive it. As soon as you change a parameter that you're not set, that's not set as a variable, or as soon as you change the robot configuration, you need to drive the equation of motion again. Also, let's have a look at the equation of motion folder. There is a file eom.m here. And if I have a look, this is actually the equation of motion derived. You see different inertial terms associated with the masses, the load for the external load. And in this specific derivation, we don't have any beam, any specific beam, but you would see other elements here as well. This is the formulation. So TMTDyn, TCT is the constraint. If we had any, there is no constraint here, so you set it to 0. And the other side of the equation is the Coriolis forces, gravity, internal actuation unit, and DC is the PID input for a constraint or a controller if you had. We don't have any. And it just, I use pseudo inverse to handle some of problems with the convergence. And that's how it is. Okay, most of so as soon as you get the equation of motion, you can start play with it yourself. So you can rearrange the matrices that are derived. You can play with it and formulate your controller like the feedback linearization controller or a force compensator. Those are already implemented, and it actually automatically reformulate this part for you, the vector formalism for you. But you can get creative further. But the important thing to keep in mind is, if you mess with the equation of motion.m file, make sure that don't set to generate mex or generate m file in the analysis. Use old m file. So it doesn't regenerate the equation of motion for you. It uses the one that you have already edited. Or use old mex file, or use generate mex from edited m file. So you edited your equation of motion, you want to generate a mex file to improve the performance. So these basically options are provided for you. Okay, so I set it to generate a mex file, and that's it. Okay, the animation is done. Just pay attention, the animation is not part of the simulation. You can set the animation to basically you comment the animation completely, and as soon as the simulation is over, which was pretty fast, you get the post-processing result. I just wanted you to have the animation as well. So if you're in a hurry, you're not interested in animation, just have a look. I have implemented an error analysis in the post-processing file. Of course, it's specific to this specific example, so you need to play with it. But you see that I get 4%, 4.8% error, which is equivalent to mean absolute error of 2.8 millimeters. And this is how it looks. So the dashed lines are the experimental data, and the solid lines are the actual data. It doesn't look that good, I know, but just pay attention. It's in average is 2 millimeters, 2.5 millimeters, and stiff lobe is not the best to start to practice your modeling techniques for. Okay, that's it. What we get further, let's have a look. So let's say, okay, let me show you something. So I set it to know the dynamic input. I just multiply the pressure 2 times, or I don't know, 20 times. So we're gonna get, and I just, I'm not interested in the static analysis anymore, and I don't want to record it. So I don't want to bore you. And it, when I hit F5, it doesn't derive anything for you, but now it just straight away drives the equation of motion and run the dynamic simulation for you. You see the progress here. But why it does that, and we set a very large value for the input pressure, so I may end up with a stepping issue in the numerical simulation, okay? So be ready for slow simulations if you set irrational values. But just from the previous calculations, have a look here. In the result now we have 2.mat files. It saves everything in the workspace for you. So just grab it into the terminal, drop it in the terminal, and it, you see all of the plots that was generated before. And this is the video file that it basically saves for you. The first few iterations were basically the static results. And it is actually according to the real-time values of the simulation. So 1 second of that video is matches 1 second of the reality. Okay, you see the simulation with the higher pressures are in progress. It's slower, of course, 20 times the pressure. It elongates a lot and probably vibrates a lot as a result. While it's doing that for you, let me, for the sake of time, go back to the TMTDyn GitHub. Okay, I encourage you to have a look at version 4, 5, and 6. Okay, the recent ones. The latest version we worked on, you have implementation for series rigid link, absolute state, reduced order model with Bishop's frame, etc. And for example, if I show you the reduced order model with Bishop frame, for example, you see for the rotation, I define the transformation the same, but for the rotation, I use a simple curvilinear frame and a correction rotation around z-axis now, okay? And also I have a reduced order model implemented. So you can play with the examples and build up your models based on that. Apart from that, getting back to this, the Mamobot, you see a growing robot implemented, which you may find really interesting. So again, it's reduced order model. We have a reduced order model section here, but then you see that, and it uses a spline implementation of when you have different segments. So basically, the growing robot overlaps with the tendon part, but the overlap length changes. So we can implement that as a spline function. And that's basically where the spline knots or control points are located. So you see, and the length, I set it to a variable like underline sim. So it's being updated during the dynamic simulation. That's another interesting thing to have a look. And finally, the CTR model. If you have a look at the model, you see that I benefited from basically benefited from copying a single body definition, but also I set the reduced order model coefficients manually, and also I set it similar to the previous reduced or the previous polynomial care. So this way I enforce the continuity between different segments. And for the second tube, I set it completely similar. Part of the sum of the degrees of freedom, I set it completely similar to the previous degrees of freedom. That enforced concentricity. So if you have an unstable system with concentricity constraints or any like closed loop system, etc., this example can be a good starting point for you. Okay, the simulation is almost over. Yep, done. Now it calculates the animation for you. Oh, and it's gonna elongate a lot. So yeah, it diverged. Sorry for that. It obviously diverged. You see, it elongates 20 times the pressure. It basically elongates the system 4,000 times of initial length. Okay, probably I should have set it to 2, not to any.
Hadi, maybe in the time, if you can just have a look at the chat, because it seems that some students have some work with the software. I don't know if we can make some troubleshooting online directly, or if, I mean, of course, afterwards also, I don't know, by email, if there is anything that you can help with.
Yeah. Okay, guys, thank you so much for this. So let's get into to the chat. Thank you, Matthew, for pointing me to the chat. It was finished with the presentation. So it's only me. Sorry that I'm not very responsive, and a lot has been implemented, not published yet. But please get in touch. We can do a lot with it. But looking at the chat, oh, that's Sorosim. Okay, that's me. The error, PNG. Okay, yeah, you need to, yes, you need to drive the equation of motion. So you need to set the drive equation of motion, change the no to full system. You know, the version uploaded on GitHub, it has it no. It assumes that it's already derived, but just set it to this full system, and it drives the necessary elements that you cannot find. I correct that on GitHub, but anyway, pay attention that the first time you drive this equation of motion, you just set it to no. and just change the variables that you want. I actually did that, so I run it again even, but so why I get this error? I'm getting some errors too. What's this one? Dimension array being consistent. Par 4. That's weird. I have to look into it for you. It might be an issue with the parallel toolbox that you have. You know, there is a method that you can set the number of workers to be used to run the simulation, to run the derivation optimization for you. You need to call that method and set the number of cores to 0. So it doesn't call the parallel toolbox. That causes an error. I think that's an issue, but please let's talk about that later. And not Ubuntu implementation. So if just make sure you set you change no from full system. It should work on Ubuntu. I've tested it extensively on Ubuntu, and not the C wrapper for external solver. Just actually the C wrapper for external solver is in Ubuntu. So yeah, sorry, including that. Running on macOS. macOS, I have no idea. It's good to have a look. Okay, thanks. So first you have to set to no. Okay, yeah. Drive. Yes, exactly. Yeah, it seems solves everything. Sorry, I update the GitHub repository so it works straight away. But later on, just make sure you set it to no. You don't want to wait for the derivation of the equation of motion anymore. I'm trying to shut. Yeah, that's good. Yeah. Okay.
I think that's all. I mean, about the questions that I see in the chat. I don't know if there is any other questions from the attendees.
Yes, please. Shoot.
Of course, you can keep in touch with Hadi by email, so whatever. I mean.
Yeah. Here's my email if you wanted to get in touch. We can do a lot. Okay. Meanwhile, you can have a look at the simulation with 2 times the pressure. At sign KCL.ac.uk. As I said, we've already implemented a lot, most of it under preparation, under review, but definitely get in touch. I will fully support the implementations, the explorations, and would be really happy. But as you saw, the derivation phase is lengthy. I have 3 segments only here, but Federico had 10 and even 20. And there you saw a real-time implementation of the dynamic system. So I probably have to have a close look at their development, see how they're doing it that fast. But you get some flexibility here.
Yeah, sure.
Yeah, thanks so much.
Very much. I was about to ask you to type your email, but I see that you've just done this. So yeah, you can, I mean, all the attendees can contact you to ask any other questions or curiosity. Let me only conclude saying that actually today we saw probably the most advanced modeling tools that we have available so far for soft robotics. We are going to see something slightly different on Friday with Christian Durier, because it's about simulation control, so it is a different approach. But actually, I really think that you, Federico, and you, Hadi, made really a very good job into developing tools that we really need in soft robotics for modeling. So congratulations, it was really an amazing tool. Okay, I think this concludes this second workshop for today. And actually, I think that all the attendees can use the rest of the afternoon for the team working. And I will leave the floor for closing this, the 2-day sessions to Matteo, if he's online.
Yes, hello. Here I am. So again, thank you, Hadi Sadati, for your talk and for your workshop. And for the rest, the plan for the rest of the day is the same as yesterday. So you can go back into your private groups, continue with your team working, If you have any doubts on the assignments, you can reach out to Nevio Tagliamonte, who's the chair of the competition. And as yesterday, the team working session will be open until 11 p.m. on Zoom on this platform. Of course, if you want to keep talking with each other after that time, you can just, it won't be accessible here on Zoom. And for anything else, continue to email us at info@softtechrehab.com. And as soon as we have the recordings of today's talks and workshops, we'll immediately send you the link to access them. So unless there are any questions from any students in the chat, yes, I see a hand from Camilo Fuccio. Yes, Camilo.
Hello, Matteo. I've got just a question on the assignments.
Yes.
Are they, does anyone must complete them? Will they be evaluated at the end of the school?
To understand
Any
that,
group?
I would refer you to Nevio Tagliamonte. He can definitely give you a better answer than me on that. So yes.
Okay. I will contact Nevio.
Perfect. Okay. Are there any other questions? I don't see any in the chat. I had the same question. Okay. Yes. So unless yes, so Camilo, you can if you want to write to Nevio Tagliamonte and put me in the CC, or put info@softtechrehab.com in CC. So once he answers you, I will copy the answer and share it with the rest of the students, so you can all have the answer to that. So even Donatella can have the answer. Okay, I see another hand raised from Giant Unde.
Hi, I mean, I haven't received yesterday's recording, so whom should I contact?
Okay, then for all of those who haven't received it, because I think we had a couple of problems this morning, send an email at info@softtechrehab.com asking for the recordings. I will send them again to you, and hopefully by sending it to you singularly and not in a group, we shouldn't have any issues. So all the students that haven't received the recordings and the PowerPoint presentations of yesterday's speakers, please email me, or email at info@softtechrehab.com. So please do that, Wunde. Any other concerns or issues? I don't think so. Okay then, thank you all for attending our second day of our seasonal school. Have a good rest of your evening, and we look forward to starting our next day tomorrow. Goodbye.